page, we download the application. And we do this through a distributed job queue, and everyone's happy. So the data store, we are storing all of the application metadata. Specifically, this might be description, ratings, version, so on and so forth. And we're actually tracking changes over time. Secondarily, application binaries. This is for free applications. If anyone wants to write me a check to download all the paid applications, I'll be available afterwards, and very happy. Yeah, and we're tracking all of this. It's quite a big data set. It's fun. So now that we have all this stuff, what do we do? Well, you know, we have a whole bunch of mobile applications. I can only play so many games of Tetris. So we built some automated analysis tools, and we started extracting data to figure out what we're doing here. I'm going to go into detail about specifically what we did on each platform, but generally speaking, we're looking at what things, what APIs and framework constructs on a given platform and app references, what things are implemented inside of the application. On Android, what permissions are in the app, and then sometimes we can get strings out of the application if we have specific things we're looking for. So what do we do on Android? So Dalvik is not only a fishing village in Iceland, it's also the VM on Android. It's actually pretty cool. It's similar to a JVM, and it has a lot of differences that frankly don't matter to our analysis right now, but it's really optimized for mobile. The application packages for Dalvik are called APKs. They're very, very similar to jars, and APKs and jars are basically just special zip files, so they're fairly easy to extract. The main executable in Dalvik is called classes.dex, and so that's one of the main things we're looking at. The other thing of interest in an Android application is called the Android manifest, which is a really kind of proprietary binary encoded XML document that describes the permissions of an application, its components, so on and so forth. Before we kind of dive into what we did for analysis, I think a brief background in what the Android security model is. Specifically, Android has granular permissions for all of its specific capabilities. So up front, Android declares what your app's going to do, and it never goes around that, hopefully. Come at 3 to have fun. Also important is enforcement is at the process level and the VM level. So if you find an Android VM vulnerability, usually it means absolutely nothing because everything's enforced at the Unix process level, IPC level, and what your user's permissions are on the actual device, which is really interesting. So what did we do? As I said, Android has permissions. And so one, we looked at package permissions, but simply looking at permissions alone, all that tells you is if an application wants to access data. It doesn't tell you what it actually does. So we also did DEX static analysis. And so one example question we could ask is, hey, is this permission requested and is this API referenced? One example of how we can do that for the phone number, we can look at the read phone state permission to retrieve the phone number, and we look for the telephony manager get line 1 number API. And with either one of those missing, the application is not likely going to actually access the phone number. Or we can run arbitrary analysis to ask other interesting questions of the data. I think it's important to understand what we can do and what we can't do. For the assumptions right now, we're assuming that applications don't get around the permission model because, for example, if you're rooting the phone, if you're using local privilege escalation exploits, you have bigger problems than stealing your phone number. Most likely. Secondarily, capabilities can be implemented outside of Dalvik, and this is really important to understand because you can bring in native code to Android applications, and you can basically download ARM code from the internet and start executing it. And of course, in static analysis, we're not going to be looking at that. But I think it's important that everyone kind of understands what we're looking at here. So specifically, we're not looking at code downloaded at runtime. We're not looking at encrypted code. So, for example, if there's a polymorphic engine or something like that, the current static analysis that we're doing doesn't look at that. And we're also not looking at dynamic linkage. So if you're using reflection or any sort of raw IPC calls, so Android has this IPC mechanism called binder. We're not looking at raw calls there. At some point, we will get there, but we're looking at the vast majority of apps that use the framework as it's built right now. What do we do on iPhone? So iPhone, as a lot of you guys know, uses process-level sandboxing, and the App Store enforces APIs. Unlike Android, you don't usually have acknowledgement of permissions except for push and location, where there's a user box that says, hey, do you want to allow this for this specific application? What is an iPhone app when you actually download it? Like an APK, it's just a zip file. The application binary is typically in a certain place, and it's an executable format called Mach-O. Yeah, it's the same executable format as on OS X. The Mach-O, the header is a series of load commands, so they specify how the binary is segmented in memory, what frameworks it's linked to at runtime, whether it's encrypted, and so on and so forth. There's 3 segments that we're going to be caring about today: text, data, and link edit. Text is where the executable code and read-only constants are. Data is where we have the writable data or any sort of kind of things that are initialized but can be mutable. And link edit is all of our dynamic linker fun. If any of you guys are used to reverse engineering portable executable format, the top-level construct is a section, whereas in Mach-O, the top-level concept is a segment, and a segment has many sections. Totally confusing, but for whatever reason, they decided to change the terminology on us. But one of the big problems is once we download apps, they're encrypted. So what do we do? I think it's important to look at how the Mach-O, basically how the Mach-O is loaded in the kernel. So first, there's basically file segmentation, and the text segment is encrypted in memory. So what happens when you load an iPhone app? The kernel effectively decrypts that encrypted segment and maps that into memory. But we don't have keys to decrypt that right now. So if you're interested more in how this loading process works, I think there's a lot of rich research to be done here. This is all open source, available right there. So the question is, we're not decrypting the text segment. What can we see? The great thing is we get symbol tables, and almost every binary I've ever seen has very gratuitous symbols in it. So these are all in the linked edit table. They're all plain text. And the other thing we can also see is frameworks. So these are effectively the dynamic libraries. And we can actually see those because those are implemented as Mach-O load commands, so we can see that all in plain text too, which is really nice. So what did we do to analyze these apps? First, we're looking at the symbol table, which is defined symbols, which are things that are like classes and methods you implement in your application. We also looked at undefined references, so these are the things you're importing from the platform itself. And then we're looking at Mach-O load commands, and similar to what we said on Android, we're defining heuristics to say, hey, how do we know if an application accesses a device's contacts? We're looking to a reference to any of the address book APIs on the device. And like Android, we can run arbitrary analysis as well. So to understand what we're looking at and what we're not looking at, we're not decrypting the text section. And because we're not doing that, we can't look at dynamically loaded code. So for example, if you're dynamically importing frameworks, or you're bypassing frameworks to access things via private APIs, or you're downloading code at runtime, all of these things are probably going to get you rejected from the App Store anyway. So it's probably not too impactful, but these are things we're looking at in the future. So if you didn't understand anything I said, here's the summary. We downloaded a whole bunch of Android and iPhone apps, lots. And we built a whole bunch of analysis tools so we can ask really probing questions of them, against the data set in mass. Oh, and we don't want to do it manually because I don't have nearly enough Red Bull to go through 100,000 applications. We tried that. So we're going to go through some results, and we're going to do this as a series of stories. It should be fun. So the first story is, in the beginning there was data. So what happened here was when we first got this data set, we were really excited, and we asked a first question of, are there any applications that are accessing contacts on my device that maybe shouldn't be? And we were saying, oh yeah, we're going to find like 10 applications that, that stick out like a sore thumb. And it turns out that a very large number of applications access contacts on both platforms.
And one of the motivations behind this, a lot of the early variants of malware, especially on platforms like Symbian, used SMS and other
basically to auto spread.
Exactly, to auto spread. So SMS, MMS would go through your contact list and spread it either via Bluetooth or via SMS or MMS.
So we started going through this data, and we found a whole bunch of soundboards. Why does a soundboard access my contacts? I'd love it to say, Han Solo, I've got a bad feeling about this whenever John calls me, but why? So we actually, this is a disassembly. It's through a tool called Boxmolly. It's a great set of disassembly tools for Android DEX files. And we found, we have a smoking gun. It's accessing the contacts API, but what's the context? What's the context of all this? Well, turns out that it accesses contacts to set custom ringers. This is a totally legitimate use case. And the key message here is if you look at an application and it seems weird that it's accessing something and you dig in, a lot of times it's totally legitimate. And if we look at the actual disassembly output, this is the access to contacts is in a method called assign ringtone to contact. Totally makes sense, right? If I want to add a ringtone to a contact, you should be able to access my contacts. So what's the lesson? Not all apps that access sensitive data are bad.
Just to be clear, not all apps that access sensitive data are bad.
Not all apps that access sensitive data are bad. If you take anything away from this talk, please remember that. Story number 2. So we said, okay, crushing defate. We didn't find anything wrong with the the soundboard applications. But what about location? Are there any applications that are kind of using my location for purposes that I don't know about?
And what does this say about mobile apps too in the direction? Nearly 30% of every single mobile app that we saw knows where you are. It's interesting.
So we went through a search. We started looking through Android and iPhone apps that access the location, similar to how we did before. And we went through a whole bunch of apps, and every single one nearly that we encountered that didn't seem to have a legitimate use for location, but that actually accessed your location, had a third-party advertising SDK in it. And this was really interesting. So we dug in a little bit deeper, and here's what we saw. So one SDK in particular, Quattro Wireless. In the Android emulator, you can simulate the lat long. So of course, 3.1337 is where we are. I think it's somewhere in the middle of the ocean somewhere. And we Wiresharked it. And look what we found. We found an ad request to the Quattro Wireless ad server, and we have a poorly rounded version of our latitude and longitude sent over to the server. Oh yeah, and it's plain text HTTP. Even better. Yay. So we tried to zoom out a little bit and said, okay, well, this seems like almost every application that we encounter has a third-party SDK in it. Given if an application has a third-party SDK, how likely is it to access location? And we looked at that across some of the largest, the most prevalent SDKs out there, and we found that wow, there's a lot of SDKs that are accessing location. You notice a lot of these numbers are higher than the average for the platform. To put these numbers into context, I think we have to look a little bit deeper into how we analyze things. So, for example, on Android, if a developer brings in an SDK but doesn't request the location permissions, we don't say the app requests location or accesses your location because it can't. It doesn't have access to the APIs. So you notice the Android numbers for the SDKs accessing location were lower. Our analysis takes into this account. So if a developer brings in an SDK that tries to access location but doesn't actually request the location permission, the SDK doesn't get location.
And I think that it's a big credit to the permission-based model on Android and just having user privacy in mind in developing that.
And on the iPhone, it's fairly interesting. An application is only allowed to use location if there's a legitimate, I don't want to say legitimate, if there's a benefit to the user for using it. For example,
if Steve likes it.
If Steve likes it, yes. So if your app uses location-based information, this actually came out as an App Store rule earlier this year. They will actually reject your application if it uses location only for ad serving purposes, which makes sense. And so we kind of looked at third-party code as a whole, and it's actually surprisingly prevalent in applications. And one of the messages we have is developers, when you're bringing in code, understand what it's doing. Because a lot of times it's closed source, and there are a lot of novice developers developing mobile applications, and we think this is a great thing because it's so easy, and I don't like wrestling with bad development frameworks. But it also brings people who maybe aren't experienced in development and may just throw in ads to their code without thinking about the data they're collecting. And our message is that we would like developers to kind of understand the data they're gathering about their users, because ultimately users trust developers. And as a developer, you want to be responsible with the data you collect and to notify your users about that data you're collecting.
One of the most common things we're seeing is just first-time developers. A lot of developers on Android and iPhone have never written an app before at all in their life, and introducing vulnerabilities in terms of poorly written code or just bringing in a third-party SDK. They have no idea really what it does. They use one small fraction of the functionality and then expose all this other functionality.
So one SDK in particular, we want to tip our hat to them, AdMob. They've actually done a really good job in helping educate their developers on what data they're accessing. So specifically, the AdMob SDK defaults location collection on iPhone to false, and they encourage their developers to think about what the ramifications of gathering location are. I think I would love all SDKs to kind of be this up front and encourage their developers to think about things this way. So the lesson we learned here is developers don't always know what's in their apps. And we want to encourage people to, if you're developing mobile applications, really look closely at what sort of data you're collecting personally and what sort of data maybe third-party libraries you're bringing in are collecting.